Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 6, 2026, just 2 days ago. It introduces a framework for robot learning where scaling the fleet size from 1 to 4 robots accelerates the learning process by a factor of 2.4 while achieving near-perfect success rates. The paper is titled SOP, a Scalable Online Post-Training System for Vision Language Action Models. And as we'll see later, the results for real-world robotic deployment are quite significant. Figure 1 illustrates the Scalable Online Post-Training Framework, or SOP. At the top, the diagram centers on the cloud training loop, where the main policy learning happens. Connecting to this, the middle section displays a fleet of robots deployed across various locations. They upload their interaction data and download improved models asynchronously. The bottom row highlights the diversity of this data, showing real-world examples like folding clothes and assembling boxes. So Figure 2 breaks down the specific architecture governing this process. In the center, a distributed fleet of robots operates across different tasks, like the grocery restocking or laundry folding shown on the left. These robots continuously stream their experience data, represented by the large arrow at the bottom, into the cloud server on the right. There, an adaptive sampler mixes this new online experience with a static offline buffer to stabilize training. The generalist learner then updates the model and streams the fresh policy parameters back to the fleet, closing the loop. Alright, while the previous figure mapped out the system physically, Algorithm 1 defines the exact logic driving it. The process starts with an initial policy and an offline buffer. 2 key loops then run in parallel. First, the actor section shows how each robot executes the policy to collect rollouts or records human interventions if a person takes control. Meanwhile, the Cloud Learner section asynchronously samples mixed batches to update the policy parameters, which are continuously streamed back to the fleet. Okay, moving from the algorithm to the real world, Figure 3 displays the 3 experimental task families. The top section, labeled A, covers grocery restocking. It spans diverse scenarios, ranging from shelf organization in A1 to opening freezer doors in A3. Below that, Panel B demonstrates laundry folding, where the robot uses both arms to manipulate a deformable cloth. Finally, Panel C at the bottom shows box assembly, which requires precise coordination to fold a flat cardboard sheet into a structure. So, with the tasks defined, Figure 4 presents the core results. The top row compares success rates across the 3 domains. You can see a clear progression. The gray bars represent the pre-trained baseline, the blue bars show standard offline methods, and the orange bars highlight the proposed SOP system. SOP consistently dominates, achieving success rates up to 98%. Meanwhile, the bottom row illustrates throughput, showing that the system isn't just reliable, it's also much faster, more than doubling the tasks per hour in laundry and box assembly. Well, Figure 4 demonstrated the system's effectiveness on specific tasks. Now, Table 1 breaks down how performance scales when we add more robots to the fleet. The first column tracks the number of actors, increasing from 1 to 4. In the middle, the success rate after 3 hours clearly rises with more robots, reaching over 92% for the 4-actor team. Most impressively, the last column shows the time to target drops from about 174 minutes to just 72 minutes, which confirms that adding robots provides a near-linear speed-up in learning. So, while Table 1 focused on scaling the robot fleet, Figure 5 shifts focus to the pre-training data scale. The chart tracks success rates over 3 hours for models initialized with different amounts of data. The orange line, representing the full dataset, starts strong at 61%, while the gray line below begins significantly lower. Crucially, the shaded area between them shows that this data scale advantage persists, meaning post-training improves all models, but doesn't erase the benefit of a better starting point. Wrapping up, 2 takeaways stand out. First, tightly coupling fleet-scale deployment with online learning effectively bridges the gap between general pre-training and expert proficiency. Second, the linear speedup from adding more robots suggests that scaling physical data collection is just as critical as scaling compute. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.